Hi, my name is Joe Alexandersen and I'm an assistant professor at the unit of mechanical engineering at the University of Southern Denmark. Today I'll be talking about topology optimization for fluid thermal systems, more specifically focusing on heat sinks and heat exchangers. So my research work focuses on what I call multiphysics simulation and optimization, which is quite a broad topic, partly because we have multiphysics in there, but also because it covers both simulation and optimization. So as we'll be talking about today, that covers electronics cooling and heat exchanger design, especially in the context of optimization methods. But I'm also interested in micro and millifluidics, turbulent and time-dependent flows, high heat flux cooling and other components for fusion reactors, as well as process simulations of casting and welding processes. So what I'll be focusing on today is so-called simulation-based design optimization, where we couple simulations and optimization theory. So here we see a complex model of conjugate heat transfer in an electronics enclosure. We couple that with mathematical programming or gradient-based optimization. And by coupling those two things, we get a piece of software that is able to optimize our component or a structure for a given physics with respect to a given figure of merit. So why do we want to optimize? Why spend the time on doing this? Well, one thing is it can reduce the time from idea to product because it can cut down the iterative design process. But why optimize at all? That is, we live in a world of diminishing resources with an increasing population and increasing consumption. All outlooks seem to just be pointing upwards. Especially now we're introducing an increased electrification of our society. With that we have increasing power density and performance of electronic components. And with that we have higher thermal issues, higher amount of wasted heat that we would like to either not waste at all or at least reuse for other purposes. So that's why we need to optimize. We need to minimize material use. We need to minimize energy waste, or that is maximize the efficiency of our systems, of our entire society in principle. So the particular simulation-based design optimization method that I use mainly is topology optimization. And this is a hot topic. You'll see pictures like this pretty much everywhere these days. You see it used in industry, you see it used in academia, you see it used by makers on YouTube and all these kinds of things. And that's because for structural mechanics, topology optimization is now broadly available in commercial software. And it'll be called various different things. Some of them are different names for the same thing, and some of them are names for different methods to do the same thing. So you'll see specifically generative design is very popular these days, and that is usually based on some kind of topology optimization in the center of the generative design process. So topology optimization is an extremely strong tool, partly because it can be used on a lot of different physics, which is perfectly exemplified by looking at the broad portfolio of Ole Sigmund's group at DTU. We see that we can use it for mechanical structures, large-scale structures, bridges, and airplane wings for mechanical purposes. We can use it for hierarchical structures, biomechanics. We can use it in acoustics, nanophotonics, and of course we can use it for thermal problems and conjugate heat transfer problems, which is what I'll be focusing on here today. So if you look at traditional heat sinks, they are often very, very simple, and there's a reason for that. These are very cheap to manufacture. These ones you can usually just extrude and you can cut them off to length, or you can slice using different things. You can cut them out using a milling machine. There's a lot of ways of doing this, but they are usually very cheap, and if you choose correctly based on potentially some correlations or some simulations, you can actually get a pretty decent performance, especially considering the very low cost. But where topology optimization or simulation-based design in general makes sense is applications where a highly customized cooling heatsink or cooling solution in general can be applicable. You can win quite a lot by adding this high design freedom that we get from topology optimization. So we have some different mechanisms of heat transfer: forced convection, natural convection, and diffusion. I've primarily focused on natural convection, so that's what I'll mostly be discussing today, but I've also started working a lot with forced convection recently as well. So just to show an example of this iterative design process, so topology optimization is an iterative process. It doesn't just give you the answer straight away. You kind of have to do many iterations after each other, and that means a lot of simulations. So what you see here in the video here, every frame of this video is one simulation. So we usually take anywhere from maybe 100 to 1,000 depending on the difficulty of the problem. So that's quite a lot of simulations in a row. So that's why we also need very efficient simulation tools for making these optimizations plausible, even in an academic context, but especially in an industrial context. Here we see an example. So this is a heatsink inside a closed box driven by natural convection. So we have an electronics chip or heat source down here. The gray box, we can add solid material to conduct the heat away from the heat source. And then we have cooled the outer walls to help aid in the transfer of heat. And here we see 4 designs for an increase in chip power, increased dominance of the natural convection. We see that we go from long straight fingers conducting the heat away from the source out towards the cold walls. And then as we increase the dominance of natural convection compared to diffusion, we see that these fingers begin to curl up, contract towards the heat source because they no longer need to be as long to transfer the heat away. It's more efficient to use the convection heat transfer that occurs due to the circulating air or water or whatever the cooling medium is. However, like I said, this is an iterative process and it can be very costly. So these are very large 3D simulations. These particular ones have 40 million degrees of freedom for a quarter of this domain. So we impose quarter symmetry. And that for 500 design iterations, so that is 500 simulations essentially, takes around 10 hours on 12,800 cores. So here we are using a small supercomputer for half a day and to get our result. So not everybody has access to a supercomputer, unfortunately, but that's why we need to make these methods more efficient, and we might need to introduce simplified models in order to make this applicable in an industrial context. And I'll get back to that later in the presentation. So next step was to use this developed framework for an actual industrial problem. And we did this together with an industrial design company who worked with the design of passive coolers for LED projectors, where their idea was sort of to incorporate the cooling heatsink design as part of the lamp design, actually to make it both aesthetically pleasing but also functional in terms of cooling the LED package, which gets quite hot, and particularly for LEDs, the warmer they get, the lower the light output is and also the lower the lifetime. So if you're able to cool the LED packages efficiently while still having a aesthetically pleasing design, that would be excellent. So the design company focused on these lattice type structures, partly because they were self-supportive for additive manufacturing. So these would not be producible using conventional methods. But what we wanted to see was what can topology optimization do for this problem if we just let it have the full design freedom that it can use. So here we see 3 different designs. So the first two here are for a horizontal orientation, so that is you turn these 90 degrees and the light is shining in the horizontal direction. And then this last one is for a vertical use case where the light is pointing straight down. So these designs are optimized for those particular situations, for a particular LED heat output. And we see that common to all of them are actually that we see that we don't have circular fins, we don't have circular pin fins, we actually have elongated cross sections of all the members. So we have these like aerofoil type shapes if we look closely, and these are there to guide and help accelerate the flow. And common to all the designs, no matter which orientation we have, is that they all have a cavity in the center. And this cavity is very central to lowering the resistance and increasing the acceleration of the flow through the heat sink. Again, these are very large computations taking several days on a small supercomputer. So the cool thing about topology optimization is that it can generate a solution that we potentially can use, especially in collaboration with additive manufacturing, which I'll get back to in a second. But it can also help us to gain insight into optimal design in general. So we can use the optimized designs, we can use the simulations for how the flow and how the heat transfer is occurring in them, and we can zoom in and we can investigate why do these designs perform better than our conventional or reference designs, for instance. And here we see the temperature fields for these three designs here. Here's the reference lattice design. We see that the air is very fast heated up as it passes through the heatsink. So up here the convective heat transfer is very inefficient compared to down here where we have fresh cool air. And if we look at the optimized designs, we actually see that we have this open core which allows for cold air to enter from the outside and reach the top members, thereby increasing the efficiency of convection by quite a large degree. We can also look at the pressure fields, something that would be difficult to measure in practice, but simulation can give us these additional details. We can see, as probably expected for these tight lattice designs, we get a lot of stagnation zones, we get a high flow resistance, a lower flow velocity, and a lower convective cooling. Whereas for the optimized designs, we see that again, these cavities are actually there to produce at times negative pressure regions to help accelerate the flow or at minimum reduce the flow resistance. But we also see these aerofoil type cross sections that are there to guide the flow in an advantageous way. We can again see how we can draw air in here that can be used up at the top. So like I said, topology optimization can produce a final design in principle that using additive manufacturing to at least some extent we can actually produce. So here we see a specimen manufactured by Renishaw in aluminium. We used this specimen down in the lab. We set up an experimental validation of our simulations and of our optimizations. So we were actually sure that these designs performed as good in real life as they did in practice or in numerics. And it turns out that they do, so we actually see very good agreement between our simulations and experiments. And we see that our optimized design can give us a 26% lower LED temperature, which more or less directly translates to quite a significantly longer lifetime of the LED component. And that is even using 11% less material, which for additive manufacturing directly translates to cost, usually using the common processes. However, additive manufacturing in metal is still quite expensive, so we were looking at some other solutions on how these might be manufacturable. Their investment casting comes to mind, especially additive manufacturing driven investment casting. So that is where we 3D print still, but now we make the component in a wax-like material. You could even use a PLA-like material as well, but these wax-like materials are better for the investment casting process. You then make a plaster mold around it, burn out the resin or the wax, and then you have your empty space, your casting mold that you can pour liquid metal into, and then you have your final metallic part in the end. And this process is quite a bit cheaper than additive manufacturing in the same material. And what we actually observed was that these cooling geometries actually have a more or less perfect solidification behavior. So these are some simulations that my colleague at DTU, Nils Titsche, did for us at some point. And as he said, it was more or less by the book solidification behavior. And that is probably due to the analogous problem that they are optimized for. They're optimized to transfer heat away from a heat source, and it's more or less the same problem that we're actually dealing with in solidification. This also gave us very high quality castings with very low or no porosities, get overall nice surface finish, and generally this process seems to be quite promising in this aspect. But we haven't completely stopped thinking about additive manufacturing in part. So we have just received a new machine at our Sønderborg campus. So my colleague André Popa here has produced one of my designs here in stainless steel, but we'll soon be getting copper, so we can do something like this. Here it's in copper colored PLA, but soon we'll be able to make heat sinks in copper. And then I'm also collaborating with some Finnish people who are printing in a conductive plastic filament. And there we're trying to see how does the optimized designs actually differ when we have a conductive material, yes, but still substantially worse than using a metal. However, potentially quite cheaper and a little bit more broadly applicable. However, our 3D additive manufacturing in metal process is also pretty cheap, so I think costs are overall coming down on these processes. So, like I mentioned several times here, the computations are very expensive, they take a long time, and we have to use supercomputers when we're dealing with these complex multiphysics problems, with flow being coupled to heat transfer, for instance. So you could say we want to move towards the desktop, and that's sort of equivalent to going from academia to industry. Not a lot of industrial companies have access to clusters, although cloud computing is taking quite a lot of leaps these years, so potentially it would be possible in the near future for industry to book time on these supercomputers. But we would still like to go towards something where maybe not, again, not as fast as this animation shows, but at least during the day, an engineer can set up a design problem, start the process, and he can follow along interactively during the day, and then when he comes back the next morning, he has a final design. That is not that easy, but we might be able to do it introducing simplified, but yet still accurate, or at least accurate enough models. So this is sort of the traditional engineering way of thinking. What can we cut away, and what can we keep in our model to make it as simple as possible and as easy to solve as possible. So we introduced a potential flow model at some point here for natural convection, where we could reduce from 5 to 2 degrees of freedom per node, so that's quite substantial, and we could go from essentially something that took 9 hours on 500 cores to something that only took around 13 hours on 40 cores. And 40 cores, that's a high-end desktop workstation that is within the realm of sort of industrial use. So I also tried to apply this method to an entire electronics enclosure. So instead of just looking at one heatsink, one component, looking at the interaction of multiple components. So the example here is a vertical electronics cabinet. We have these very complex interactions between the natural convective plumes from the various electronics components. So we have a large degree of coupling. And the question here is, for cases such as this where things are interacting, are standard heatsinks sufficient? And should every heatsink be the same? So should we have the same one here, here, and here, and here? So I set up a simplified problem where we have four chips or heat sources of the same size, same heat output. We have a skewed inlet and outlet at the bottom and the top. And then inside the green, we can place material to design the heat sinks. So using this potential flow model we introduced, we get a design out here that we can see is mostly pin-like fins. So pins with some secondary branching on them. They're mostly straight, and there's more or less even distribution of the material between the four components. So I actually allowed the optimizer to place uneven amounts of material on the four if that is so desired. So the problem here is if we actually look at the flow. So this is a potential flow model where we've essentially thrown away inertia. And that actually leads to an artificially even distribution of the flow. You can see the flow enters here and is very fast distributed among all the four components. And we see that we have the largest velocities between the members. If we then try to simulate this design, so this design optimized using the simplified model, using a full Navier-Stokes model, we see that the flow field is completely different. And that is because for this problem, inertia is dominant, and that's what we've thrown away. So of course our simplified model is not as good as we could have hoped. And we see that the largest velocities are concentrated along the diagonal here. And also that the cold air is not well distributed, so when we evaluate the performance, it's not as good as the optimizer thought based on the simplified model. So if we then optimize using the full Navier-Stokes model, we get these elongated fin cross sections like we've seen before. They're curved to accommodate the flow here we see. And we see that there's more material used on these two that are away from the main flow diagonal, which makes sense here, slower velocities. So we need more conductive material. The BO number will be lower here and the BO number will be higher here. So we need less material because we can rely on convection. And we can see here that the cold air is more well distributed. We allow some cold air to reach up here, and so on. So how to proceed to even larger heat fluxes or higher velocities? And that's usually where we get transient behavior, so things become unstable. So all you've previously seen has been steady state analyses. However, some problems will be transient. So that could either be because of instabilities of the flow or due to the geometries, for instance, but it could also be due to fluctuating temperatures or fluctuating inlet velocities and all these different things. So we need time-dependent solvers and optimization methods using these solvers in order to treat some of the real industrial flow problems that are very common. And this is just so expensive computationally. You could imagine if it takes a few days handling a steady state case, handling a time-dependent case could easily take months with the current approaches and the current technology. So that just isn't feasible right now. So we need a combination, in my opinion, of higher performance computing and simplified models. So one way to simplify our models could be to reduce the dimensionality of the model. So here we are working with a three-dimensional cooling channel with a heatsink inside, but we assume that the heatsink is extruded. The geometry has a constant cross section extruded in the Z direction. And then we can make a pseudo 3D model that essentially just has a 2D plane model in the center coupled to a 2D model of the heat source layer. And then we can design and simulate in the two-dimensional domain. So our problem that we wanted to tackle here was that we wanted to minimize the temperature after a short time. So instead of a steady state problem, which essentially is at infinite time, we wanted to minimize the temperature after a short time, so what we call instantaneous performance. And this requires a time-dependent simulation. Even though we're not going to be simulating for a long time, it's still more computationally expensive than a steady state model. And that's why we introduced this pseudo 3D model concept by Herdel et al. Into the time-dependent simulation domain. So here is a design optimized for the instantaneous behavior. We see that we get these sort of thick, stubby features that we see here, designed for some different cases compared to some reference designs. And we look at this short time span, and we basically try to minimize the temperature after only 1 second of operation here. And this is improved by optimizing compared to these regular straight fin heatsink designs. If we then compare to what you obtain for optimizing for the steady state, or again that's equivalent to infinite time, you get these much more streamlined features, thin aerofoil-like cross sections that we also saw earlier, also steady state problems. So this makes sense because here you want to sort of reduce the fluid resistance, so you want to maximize velocities, maximize convective heat transfer, so you need these types of shapes. But if we look at the short time span, we see that the stubby fat structure performs much better in the short time span as designed for. But if we look at the long time span, we actually see that of course the steady state design performs significantly better. We see this region where the instantaneous design is better than the steady state is not for very many seconds, but that doesn't really matter because we are interested in the short time span behavior. So up until now I've been focusing on heat sinks, so that's where we transfer the heat from a heat source through a solid heat sink and then transfer the heat onwards to an airflow. Now we want to look at heat exchangers, and that's in this context where we are exchanging heat between two mediums, or first of all here two fluids, as we see here to the left. There's some work I did together with my colleagues at DTU, Kasper Andresen mainly here and his students, and then we can get these very complex shapes that I'll come back to later in the presentation and discuss in greater detail. But first I'll talk about some of my more recent work, which is looking at heat exchangers with parallel plates. And that's parallel plates filled with a PCM or a phase change material. So here we're not exchanging heat between two fluids, but a fluid and a solid phase changing medium. And this is in the context of the EUDP project, Next Generation Ventilation, which just finished, but I still have some derived projects from this that I am finishing off, and I'll talk a bit about that now. So the motivation of this project is to design climate modules for building ventilation systems. So essentially you use these phase change material plates as a medium to store heat and to help heat up air or cool down air by having it solidified or liquefied. So we're passing air through these two stacks of plates, and this signifies our parallel plate heat exchanger. So this problem, if you want to simulate it, is inherently very difficult. So we have time dependency due to the phase change. Also because we'll have quite high flow rates, so we'll have instabilities, we'll have turbulence, we'll have a large span of length scales, so the spacing between these plates on the order of millimeters, where the whole thing is on the order of meters. So the mesh will be very heavy if we want to resolve everything. So that's where I thought of the recent trend in topology optimization, which is to sort of use these simplified models that I also discussed earlier as a way to reduce the computational time. And my idea was sort of to approximate these stacks as a porous media, essentially, so we could make a simplified model where we don't have to resolve all the details. So what I did was I went actually back to the origin of topology optimization for fluids, where you can derive a resistance term from the out-of-plane viscous resistance, and you can introduce that in a plane model. This model that they derived turns out it only works for topology optimization, so that's where we have solid regions or fluid regions. Then by augmenting it with a mass conservation based on varying spacings, which is needed in order to model the flow from these big ducts into the small collection of air gaps, and even also the flow between the air gaps, we need to fix the mass conservation, which now allows for a topographical model of these fluid models here. So that essentially allows me to take this fully three-dimensional structure here with very small details and transfer it into a two-dimensional plane model, where here we will add some resistance terms inside the stacks. So the stacks, they are two stacks of plates that are parallel to each other, and in each stack we have 24 plates and 25 spacings. And then we can compute based on a spacing of 3 millimeters. We can use this derived friction term. We can find the resistance. And because all of these are in parallel, these are also, the resistances are also in parallel, so we don't need to do anything fancy. So we can take this representative cross-section of our flow domains. We can add our resistance term from the small spacings. We also have a small resistance term out here because these ducts are still finite in length in the out-of-plane direction. And we can then simulate the flow through the entire system. We can see that we get very even flow through the spacings because they're so small. There's a large resistance that causes this sort of even out of the flow, which is also more or less what we've observed from experimental values. But we are actually now able to model this whole thing in a 2D model, which allowed us to basically look at how, if we changed the design of the inlet and outlet duct, how did that help with the distribution of air through the two stacks. So the model that I derived also allows me to look at single spacings with complex topographies. So if we zoom in on the PCM plates, we'll see this surface of the outer plates. So a lot of it is corrugation that is used for strength. Some of the things are there for filling the plates with PCM material, and all these features have different purposes. But all of them also affects the flow, of course, because we have these small dimples that'll affect the flow. We have these protrusions that will affect the flow, and we need to be able to capture that. And another possibility is to even go ahead and optimize the topography of this plate, because I'm sure we could optimize that such as to aid in the flow distribution. So we can take our physical topography here, change it to a field, so a field of the height between the two spacings, so the height of the fluid sheet between the two stacks. We can make an approximate version here first. The next step will be to take this actual topography. We can compare a two-dimensional plane model that we derived with a full 3D model, and it's honestly a little bit difficult to see the difference, but we see that the top one here is the plane simplification and the bottom one is the 3D model. So there are some differences, mainly here where we have a sudden expansion of the flow domain. There, because again we are making some assumptions on the flow that affects the sort of inertia of the system, or rather the ability to capture separation from the surfaces. We don't have that in our plane model yet. I believe we can add that, and then we could potentially resolve such problems here. But of course, this is a heat exchanger, so we also need a thermal model in order to model the thermal aspects and look at the thermal characteristics in time, look at the phase change, the energy storage, and such. So the first step is to derive a thermal model for the spacing between two plates, and next add a thermal model of the plates themselves, in which we can add the PCM materials. So these are a continuation of these sort of solo 3D approaches originally proposed by Hertel, and others have carried on in that tradition since. So adding the temperature, we can estimate the plate surface temperature. Here the distribution looks very good, but actually there's an issue with the scale. If we look at some lines across here, we see that the flow is pretty well captured. Of course, we do have some disagreements, especially here in the center, which is here with the sudden expansion, but that is tolerable. We also see that the temperature more or less captures the right level at the two ends, but there is some thermal characteristics at how fast the thermal boundary layer is developed that is not captured in the model currently. So that's something we will need to fix. So this topography model can not only be used to simplify the simulations of these complex geometries, but we can actually also use it to optimize these topographies of the plates. So here we have a problem that is inspired by this flow distribution problem. So it's an academic example. We want to take a uniform flow here, or a fully developed flow here in a small channel, and then by designing the topography, so designing the distribution of the thickness of the fluid sheet here, we want to get as even an outflow here at the outlet. So one of the results we see here in black, we see the streamlines. We have quite a good even distribution along the outlet. We have a very non-constant thickness distribution. So this can be a little bit hard to interpret. So if we look at it in 3D, we can see the topography changes. So we see, of course, we'll have inertia from the flow coming in the inlet here, so it wants to continue. So here we have a narrowing of the fluid channel. So we push the air through here where we have a higher height, less resistance, so we get more air down here. Of course, we don't have zero thickness here, so some air will still pass through here, as we also see here. So we get quite a good even distribution on the outlet. So as with all of these simplified models, there are some simplifications, and there are, of course, some limitations due to that. And one is separation here. So actually we can see, if we look in this area here, we have that if we compare the 2D streamlines, which are the green ones, with the 3D streamlines, which is the red, you can see that there is overall very, very good agreement, except in this area. And if we look at the fully three-dimensional flow fields here again in red, we see that we have this sort of swirl flow here. So it's not recirculation flow as predicted by the two-dimensional model, but we have these 3D effects that of course cannot be captured in the two-dimensional due to the assumptions that we have made. But we can still see that in the region that this swirl happens, we get recirculation in the two-dimensional model. So potentially we can add into our optimization that we want to discourage that. And this type of effect is also seen here, where we have some flow separation here from our experiments. We know that there are three-dimensional effects going on in this area, as is there here at the exit. We get some three-dimensional flow effects which are not captured in the plane model, but overall the behavior is pretty good. So finally, I want to just touch upon this shell and tube heat exchanger design. This, like I said, was developed at DTU with my colleagues and some students who worked on it. So we have cold water interacting with hot oil. We start with some simple tubes here. We have some inlets and an outlet for the cold, and the hot oil is moving around these solid channels. Here we see the optimization process. So we start with something resembling the reference design, and then we get more and more complex features. We get a lot of these protrusions on the surface that we've chosen to say they are microvilli-like, so they are sort of compared to some of the biological structures you see. So we have these small, essentially these are pin fins or something to that kind, that are aiding in the heat transfer between the solid shell and with the hot oil that is moving around it. And if we lower the conductivity, which could be using a conductive plastic like I discussed earlier, we see that these small intricate features are no longer present, and that's because we now need to rely on convection here to extract heat from the surface. We now get sort of these serpentine channels forming instead, and we still improve according to our baseline design. These are some crazy results based on another paper from Florian Fepong, but these are results from Kasper Andresen. I have nothing to do with these, they just look really cool. So we see here how we can design a cross-flow heat exchanger with the hot flow and the cold flow interacting together. And here we can see some videos on how the flows pass through each other, always separated by this solid structure or this solid shell. And of course here additive manufacturing is strongly necessary in order to make these designs realizable. So we're also working on that. Kasper's working on that. I'm working on that, and we'll try to get something cool out of that. So with that, I'll finish up here and with a list of some of the references here. And there's our review paper from last year is a good source to get an overview of what has been going on. And also my website, I have links to my publications, some videos and other stuff. Thanks.